Welcome everybody to Weekly Quantum World Detangled, Season 3, Episode 4. I am joined by my sponsors and friend Denise Ruffner.
Hi everyone, Denise Ruffner coming to you from Southern California.
I'm John Levy. I'm the chair, CEO, and co-founder of a company called Seeqc, which stands for Scalable Energy Efficient Quantum Computing. We spun out of a company called Hypris, where I was the chair for about 8 years. Hypris began life as the superconductive electronics division of IBM about 1 million years ago. So we're based in Elmsford, New York, not far from Yorktown Heights, New York, the world center of IBM's research. And we operate not only this new Millikelvin test center where I'm sitting, but across the street, we actually operate a chip foundry as well.
And John, before we get to know Seeqc a little better, let's get you to know a little better. And you have a rather long and illustrious career behind you with an MBA from a small school up north. You worked in networks and finance and biology, I believe, now in quantum. What's kind of your personal journey and your personal vision on your journey, where you come from, and how did you end up in a lab in front of two fridges?
I mean, look, it's really funny. When I was 10 years old, I was starting my first business. And really, I was kind of wired for doing that. I would run neighborhood fairs and invite kids and set up rides and have prizes. And I'd make a bunch of money and recruit people, et cetera, to do all this with me. And so I've been starting businesses ever since I was younger and worked my way through college doing that as well. And I got involved in technical companies, a long time ago. I ended up working at a place called Interval Research, which was a think tank in Silicon Valley funded by Paul Allen, and became the first CEO of a computer vision company called ePlanet, which was invested in by both Paul and Intel. And I've been working on kind of deep tech technology ever since, either from a managerial and founder perspective or as a VC. So I've helped to run 2 venture capital funds and lead the technology practice. So I've kind of gone back and forth.
And I always try to find out something personal about our guests.
Right.
Struggling with you, didn't find any hobbies, no real mentions about your personal life. What does John do and enjoy when not building quantum technology?
All right, so you got me at springtime, and next week I am going down to Florida with my wife, and we're going to the end of spring training and the opening of baseball season down in Florida, because I can't miss it. So I am a huge baseball fan.
But what I wanted to do today is ask you some questions about your company. And, one of the places I always start is funding. And it looks like you had a very healthy seed round. And you've raised around Series A, and you have a total of 29 million in funding.
Mm-hmm. Yeah,
maybe you
right.
could tell us
about 30 million. Yeah.
A little bit about your investors.
Yeah, we have a great group of investors. And what's really interesting about our group of investors is there was a time in quantum computing about 5 years ago, maybe 4 years ago, when it felt to me like there were some of the first big venture investments. And in the venture world, there's a whole idea around momentum, where a couple of big investments are made and suddenly all the other venture capital firms start looking at it. And so there was that period of time, but we weren't really ready to spin out from Hypris at that point. So we did that after that first round of big venture investing. And so what it did was, and because of what we're doing is extremely technical, it required that we had venture funds that really understood what we were doing. So, an example in our seed round was a group called Cambium. So Cambium is led by a guy named David Mooring, formerly the CEO of IonQ, but before then was running quantum computing for IARPA, which is like DARPA, only I for intelligence instead of D for defense, with loose connections to the NSA. And it gave Dave, incredible purview over what was happening in the quantum world. Plus he has a PhD in the right area. Plus he was a CEO of a quantum company. So when Dave left to help form Cambium, which is around high performance computing, The first company he invested in was us, because he knew who we were and what we were doing. Similarly, Blue Yard Capital in Germany had run a quantum conference in 2017, and their notion was to invest in quantum software companies, and came to realize that the missing link in the quantum universe and the quantum ecosystem wasn't around software, but it was really around readout, control, co-processing, system engineering to build a quantum computer. And like us, we don't believe that qubits are the defining nature of a quantum computer. We'll get to that later on. So Blue Yard came in. And then in our A round, we have a number of strategic investors. Merck. Merck spent 2 years with a team of 50 people across all divisions of Merck, studying quantum computing, what opportunities they had within Merck, where they should be focused, spoke to all of the major players, all the startups and academic groups to try to understand how they should collaborate with them all. And again, we were the group that they chose to invest in, and we're working with Merck in Darmstadt. Similar story with LG. LG did a similar thing, deep dive into quantum computing. And what we see is that a lot of operating companies have the technical capability to do the kind of diligence that's hard for venture funds to do. That said, we also had EQT come in, and they led our A round. And one of the things that we were attracted to them with was that they have companies with which they're associated. So for example, AstraZeneca, Ericsson, et cetera, are all related to EQT. EQT is the 9th largest private equity firm in the world and one of the largest venture funds in Europe. So what we've tried to do is to have an investor base that's highly informed about quantum computing and that also has a strong financial interest.
Well, I love the corporate partnerships. I think too often when people kind of think about quantum computing companies, they think they're fully funded through venture capital firms. And there's a lot of other ways to get funding. And I think corporate partnerships is very strong because it kind of gives you a customer or a place to test your ideas. So I think it's a very great relationship.
Yeah, and it goes right with our business strategy. So our business strategy is on building application-specific quantum computers, where we are working with software vendors in this kind of ecosystem that we're in the process of building, and it's all about that. It's creating those very close relationships with our corporate investors and our partners and customers.
That's great. Now, one investor I saw was New Lab, and
right.
I guess you and I met at New Lab many years ago in a different lifetime when I was with IBM. And maybe you could tell our audience a little bit about New Lab.
Yeah, New Lab is an amazing facility. And again, I use the word ecosystem because it's really that. So what a couple of guys did was they essentially got the rights to acquire or lease, I think a long-term lease, an old naval shipbuilding facility that was used, during the war, during World War II, and it's a huge space, and they've turned it into like an incubator space, but it's an incubator space for companies that are building physical things, typically, and it's based in Brooklyn, New York, in the Brooklyn Navy Yard. It's very, very industrial, and they've done a fantastic job. Sean Stewart, who runs it, who's the CEO, has done a great job reaching out to large companies, the U.S. government, and academia, and bringing them all in as partners, and then making it a kind of convening space to work on things like quantum computing. So I think we've had like 3 or 4 conferences, each one with a different theme, one of them sponsored by IBM. In fact, I did a presentation, so that's when you first probably heard of us. And it's just a fantastic platform or ecosystem for entrepreneurs of all kinds. And they've been very, very helpful. In fact, they linked us up with the team at Google, frankly, who've been interested in what we're doing.
Cool. So anybody who's watching, check out New Lab. It really is an amazing building. It really is giant. They've rehabbed it. it has a couple floors. They have spaces for different companies. It's amazing.
And they're doing more. They're expanding in Brooklyn, but they're expanding in Detroit. They're expanding, in fact, in other places around the world. And again, they're building an amazing community as well. It's fantastic.
So John, I wanted to go, so first of all, everybody, that's not a backdrop behind John. He's in the lab, and I really want to, I love being in the lab. So I want to lab tour in a minute. But you said qubits
Right.
are not the defining nature of a quantum computer. And I was wondering if you wanted to explain that a little bit further.
Okay, so think about, go back, let's say, I don't know, go back to 1946 when the ENIAC computer was first built. And it looked kind of like what quantum computers look like today. I mean, a little bit of a Frankenstein machine, never meant to scale. It wasn't designed to do that. But the fact is that it was never going to scale, not just because of how it was built, but because the transistor, which was the core of what was needed to actually build modern computers, hadn't been invented yet. The first transistor was developed in 1947 at Bell Labs, and then it took a number of years to develop the integrated circuit, the microprocessor, which you could then integrate into a full system. So at Seeqc, our notion is engineering around full systems. It's what we did at Hyperis in superconductive mode for other kinds of platforms. And what we noticed in the classical world was that the transistor initially was expensive, didn't work that well, kind of noisy, hard to get, non-standard designs. And it took a number of years and companies like TI and RCA and others to eventually build what were standard parts that you could order from a catalog that were very, very inexpensive. And they became the core of what became classical computing. You could then take those transistors, you could miniaturize them, you could put them on integrated circuits, you could get them even smaller, put them on microprocessors. What we think is that quantum computing is going to undergo the same sort of process. And whether this is going to be, silicon dots, or spin qubits, or whether they're going to be superconductive qubits or whatever, the process of converting something where we all don't know which one is going to win, if we think that's the thing, the process has to be that they become commoditized and really cheap and really standardized so that you can actually build scalable systems. I think it's what the guys at PsiQuantum are trying to do. It's what we're trying to do. And it's really, kind of going the next step in thinking about how do you design and even conceptualize massively scaled computers, quantum computers. Our case, we're building superconductive qubit quantum computers, but they're also hybrid because we're putting in classical coprocessors in our quantum computer. And these classical coprocessors are not CMOS. They're built of single flux quantum circuits. So these are all Josephson junctions clocked at between 20 and 40 gigahertz that are running classical algorithms. So you don't have to go up to the, to the cloud to do that. And they're all in the same dilution refrigerator. So what I mean by that, here, you asked for a little tour.
Let's go on a tour. I want to see.
Right.
Yeah. So that's what I want to see. Yeah.
Right. So this is one of our DRs, our dilution refrigerators, and we don't have it all set up here, but at the bottom of this, is where we put our qubits. And that's, let's just say we can get it down to 6.5 millikelvin, but we actually can typically we operate at around 15 to 20 millikelvin. But above that, at 1 Kelvin, 3 Kelvin, etc., we put more of our chips that we design and we manufacture in our chip foundry that operate at other levels of the dilution refrigerator. So we're using the full system. So whereas you might see racks of equipment, big racks of equipment, we don't really have that because all of our functionality, or most of it, exists within our chips. So for example, you'll notice that we don't actually have a lot of wires. There isn't a lot of complexity in our in our DRs because what we're doing is we are increasingly stripping things out because we're trying to put all of our logic, all of our quantum elements, everything inside one dilution refrigerator.
So I'm noticing A, not a lot of wires inside. B,
Right.
not a lot of hardware on the outside. I'm used to racks
Right.
of whatever, oscilloscopes or whatever it is. So the simplicity is very interesting in that you put the chips inside and you use all layers of the inside of the dilution refrigerator.
Right. So what we're doing here, I'm going to step into one of our soft clean rooms. I just want to see if I can find one here. We have multi-chip modules. So what we do is that we take, oh gee, let me just see if I've got one here. We take qubits and we mount, I can't find one here.
So John, it's never there when you think it's there.
I
So
know.
we
Well, I didn't know
understand.
to
Yeah.
ask, right? But we mount single flux quantum readout and control chips right onto the qubits themselves. So we built what are called multi-chip modules, and we connect them via superconductive bumps that and capacitance. And so what that enables us to do is, let's think of it like a sandwich, where your readout and control chips are here, your qubits are here, and they are connected. So if you think about the IBM or the Google architecture, where you need, say, 2 to 4 coax cables to connect them, and the signals go from very cold to ambient temperature and back. They're analog to digital, back to analog, right? And these, it's very expensive. There's a lot of latency and everything. We've gotten rid of all of that by having these multi-chip modules. And again, that's the approach that we're taking. It's chip scale, and it's designed to be massively scalable.
And I try to stand in for Tommaso, who can't be with us today, but hopefully again next time. I think this is worth elaborating a little bit. And I'm not sure how many of our viewers have seen a quantum computer or a lab before, but as you've hinted, right. There'd be racks of other equipment, measurement equipment, control equipment, readout equipment, a lot of cables with optics and other things going on. And that has two implications that you hinted on. It produces error, and it makes it difficult to scale. So this is the problem that you're trying to solve through your integrated hybrid architecture. How are you able to do that as a startup? I mean, this setup is very impressive. 30 million is a very impressive fundraise, but how are you able to deliver on this differentiator and this very unique approach?
So it's really the difference in some respects. It goes down to the difference between CMOS circuitry and single flux quantum circuitry. So in CMOS circuitry, you're generating a tremendous amount of energy and heat when you're putting these into systems. So for example, if I'm using microwaves and I'm sending down microwaves to help control my qubits, to nudge the qubits together to operate, properly. The problem is it works on a small number of qubits, but the more microwaves you send down, the more heat you send down, which destabilizes the system. So it's essentially like boiling the fridge if you want to scale. Single flux quantum circuits, by contrast, can only operate, by the way, in superconductive temperature. It's got to be 4 Kelvin and below. And our circuits operate between 3 and 5 orders of magnitude lower power. And we have almost zero resistance because they're superconductive. So we have much faster circuits, much lower power circuits, and they have to operate cryogenically, which is where our qubits are anyway. So it's a much more ecological, I think, more elegant approach.
John, you also mentioned at the very beginning that you co-design your hardware for specific applications, which is still quite unique in the quantum computing ecosystem. Can you talk about what that entails technically, what those areas of application are, and how does a customer access your capabilities?
Right. So first off, we're not trying to get a lot of customers. We want to work very intensively. We are working very intensively with just a few customers, which is why it's aligned. Our business strategy and our technical strategy is aligned with our fundraising strategy. So it's all kind of cohesive. But But generally speaking, what we're doing is and I should say also, we're not full stack. So we are not developing an operating system. There are plenty of fine operating systems out there. We're not developing applications. There are some really good applications developers. So what we're doing is we're putting together application developers working on operating systems with our platform. So think of it like an AWS kind of platform. And we're co-designing based on the very specific algorithms. Because we have a chip foundry, and because we can give people controls down to the metal layer that they couldn't get in any other way, if we co-design our applications, our software partners are able to get more control over the environment that we're giving them, so that they can make it better match their algorithms. And so we've been working actually on a presentation about this topic recently, about the advantages of building in this way. Now, frankly, this is not a long-term strategy. This is a kind of go-to-market strategy. I think the long-term strategy that companies like Google and IBM and others are taking is right to build, try to build fault-tolerant general-purpose quantum computers. Our sense is it's going to take a really long time to do it. So let's try to narrow the problem set, minimize the resources that are needed to run that, do it on a scalable design, and hopefully within a short period of time, we'll have enough working that people will understand that the architecture that we have built will scale to the complexity of the problem they care about. And so that's really how we're interacting with our corporate partners.
And before we get to our quiz to wrap this up, I'll have a second attempt to nail you down on a more specific answer in terms of areas of applications. Sure. I had the privilege of meeting some of your team, Katie, who is a quantum engineer, I believe, and very impressive, your co-founder, Oleg. What are those areas where you see opportunity, and what is your roadmap for the next 3 years or whatever horizon you would put around it?
So it's not going to surprise anybody if I say that we're working with companies like Merck and others in areas around chemistry, materials, pharmaceuticals, et cetera. That we understand that. With LG, it's highly likely that battery technology is really important to them, and so that's important. Financial services, these are all look, these are generically the areas where I think most quantum computing companies are working. In our case, I think we've put together, or putting together, a really interesting ecosystem of, again, application developers, operating systems companies, and us to be able to do that with our corporate customers. But it's also interesting. One of the things we have learned, and it's really worth kind of exploring, is that all problems which are classically intractable are not by definition quantum. And I think people have this misperception, and it goes deeper than that, which is that things that look like they are quantum, so if you look at materials or chemistry that appear as quantum problems because they are in fact made of quantum bits, if you will, are also sometimes not amenable to a quantum solution. And so one of the things that we have been spending a lot of time on is looking for problems which are, and we've done it, which are high value problems which are amenable to a quantum solution, and which are not merely intractable classically and of high value. And so that's one of the areas we've been spending a lot of time. My co-founder, Matt Hutchings, based in London, is leading that effort. And I think it's really an important point to make, because I think, again, most people will tell you, oh, it's classically intractable. You should be able to do that on a quantum computer. And it's just not true.
Fascinating. And while I live in Miami, I think everybody knows that I'm from Europe. Europe has a more co-design, hybrid-focused approach to quantum computing, slightly different flavor, also with on-premise rather than cloud. Which is the predominant strategy in the US. So exciting to see your approach. Let's wrap up with our little quiz. 6 rapid-fire questions and 6 rapid-fire responses from you, John, between 1 word and 1 sentence, if you accept the muscle-bruised quantum questionnaire challenge. Let me know when you're ready.
I guess I'm ready. Or
Good, let's do it.
Or not.
We'll see. John, who is your favorite scientist?
Oh, I guess Einstein.
Entrepreneur?
I know it's boring, but, yeah.
He comes up a lot, yeah. Who is your favorite entrepreneur?
That's an interesting question. Well, maybe it's Paul Allen.
Why? What's your most desired quality in an entrepreneur?
I used to work with Paul, so, sorry?
What is your most desired quality in an entrepreneur?
Tenacity.
What is your most desired quality in a scientist?
I was about to say curiosity, but that's pretty obvious. I think creativity.
Creativity is something that came up on our last episode, and I like tenacity. We haven't heard that before. You've worked in many different industries and fields. What do you appreciate most about working in quantum tech?
I think the ultimate impact that we're going to be able to make on not everything, as I just was saying, but on a lot of things that matter.
And the last three questions
and that I care about.
We'll dig in on that. What is your favorite quantum tech application? And it doesn't have to be computing. It could be anything else within quantum information science.
Yeah, I mean, the thing that I hope for is being able to build a quantum climate model. Yeah.
And that would be my next question, your quantum dream. So that's around climate change and climate models.
Yeah.
What would be your quantum nightmare?
That it gets used for trivial purposes. Things that really don't matter.
And the answer to the last question is now obvious, but maybe you have a second favorite answer. Imagine you wake up tomorrow and you come into your lab and magically you have a universal, fully fault-tolerant quantum computer. Who do you give it to?
I'd give it to, yeah, I mean, it's related to climate science. So I would give it to climate scientists. Yeah.
Elon Musk announced a $100 million X prize for carbon extraction in the next 5 years. And I put out the challenge on Twitter to our quantum tech community to get on that. Hopefully somebody will have the tenacity and creativity to look at these big problems. John, it was a pleasure.
Thank you so much. Thank you for inviting me, and I'll put out the invitation if you want. I'd be happy to give a tour of our chip foundry, because I think that your viewers and followers might find that pretty interesting to see.
That would be great.
Yeah.
Thumbs up from me. Thank you so much, John.
Thank you.
We might come visit in person as soon as we're all vaccinated. John.
Yeah, let's make this like in person. I agree with that. I think I'm like enough with the I mean, it's why I'm here, right? Enough with Zoom.
We look forward to meeting you and more folks of the Seeqc team. This concludes Weekly Quantum World Detangled, Season 3, Episode 4. You are now detangled. All right.
John, that was great. Thank you.
Thanks. That was really fun. I'm happy to